All right, let's dive in. Today, we're talking about something absolutely critical in system design, the distributed rate limiter. It's that unsung hero, the gatekeeper that decides if your app handles a traffic spike gracefully or just completely falls over. So yeah, let's get into it. Okay, picture this. Your app, it just went viral. Awesome, right? But wait, suddenly 10,000 login requests are hammering your API in a single second. Is this your big break? Or is it a DDoS attack that's about to crater your entire system? That moment right there is exactly what we're going to break down. So, how do you handle that chaos? Well, the answer is rate limiting, or what some people call throttling. And look, this isn't about just slamming the door on users, not at all. It's about being smart, about controlling the flow of traffic so your system stays stable, fair, and actually usable for everyone. Let's dig into why this is just so important. So, what is a rate limiter, really? The best analogy is a bouncer at a popular club. Seriously, it's the gatekeeper that's checking the list. It controls exactly how many requests get into your system over a certain period. So, if the rule is, say, 100 requests a minute, the rate limiter is the one enforcing it. You hit 101, sorry, you gotta wait till the next minute starts. Okay, so why is this basically a non-negotiable for any modern system? Well, first up, security. This is your frontline defense against denial of service attacks that are just trying to swamp your servers. Second, and this one's a biggie, is cost. Unchecked API calls to paid services, those can lead to some seriously scary bills. A rate limiter puts a cap on that. And finally, it's all about stability. It's how you filter out the noise, misbehaving bots, buggy clients, so that the real users have a good experience. All right, to build a good rate limiter, you can't just pick something at random. You need the right tool for the job. And that all starts with understanding the core algorithms. We're going to look at 4 main ways to do this, and each one has its own pros and cons. First up, we've got the leaky bucket. I love this analogy. Just imagine you're pouring water, requests in our case, into a bucket that has a tiny hole at the bottom. No matter how fast you pour water in, it only leaks out at one steady, constant rate. This is amazing for smoothing out spiky traffic into a predictable stream. But if the requests come in way too fast and that bucket overflows, well, those requests just get dropped. Next, we have its cousin, the token bucket. Now this one's a little different. Instead of an empty bucket, you start with a bucket that's full of tokens. Every request that comes in has to spend a token to get processed. And those tokens, they get refilled at a nice, steady rate. The big deal here is flexibility. If you've got a bucket full of tokens, you can absorb a sudden burst of traffic, which is perfect for APIs where you don't always know when a spike is coming. Then there's the fixed window counter. This is probably the most straightforward way to do it. You just chop up time into fixed blocks, like 1-minute windows. You have a counter, and you just count the requests in that minute. If it goes over the limit, you say nope to any more requests until the next minute starts. Super simple, right? But it has this one really nasty flaw right at the edge of the windows, which can actually let twice as much traffic through as you intended. Whoops. And that's where the sliding window counter comes in. It's the clever fix for that fixed window problem. Instead of just looking at the current 1-minute block, it looks at a rolling time frame. It kind of peeks back into the previous window to get a more accurate picture. This smooths out those bursts at the edges and gives you a much more fair and precise rate limit. It solves that double burst problem completely. Okay, so that's 4 different algorithms, but which one should you actually use? It's not always an easy answer because it's all about trade-offs. Let's put them head to head and see where each one shines. Yeah, it really is all about picking your poison. Leaky bucket, super smooth, predictable output, but it hates bursts. Great for something like a payment gateway. Token bucket, it loves bursts, super flexible, perfect for a social media feed where people are refreshing like crazy. Fixed window is easy to build, but it can be unfair, like we saw. And sliding window gives you that sweet, sweet accuracy, but it's more complex to implement. The bottom line here is you have to match the algorithm to your traffic pattern. There's no one-size-fits-all. Okay, so we've got the theory down, but knowing the algorithms is just half the battle. How do you actually make this work across a massive distributed system with servers all over the world? That, my friends, is a whole different ballgame. Let's talk about taking this to scale. So here's the million-dollar question. Let's say a user gets 10 requests per minute. Easy, right? But what if their requests are hitting 100 different servers behind a load balancer? Server A has no idea what server B just saw. How do you keep the count straight? You need a single source of truth that everyone can agree on. And this is the classic way to solve it. Your requests come in, they hit a load balancer, and get sent to any one of your application servers. But here's the trick. Instead of each server trying to keep its own count, they all talk to one central place. Usually, this is a super fast in-memory data store like Redis. Why Redis? Because it's incredibly fast, and this is key, it supports atomic operations. It becomes that single source of truth for your entire system. But using a central store like this opens the door for a really subtle, really dangerous bug. It's a classic concurrency problem called a race condition. Let me show you how this can quietly, completely break your rate limiter without you even noticing. Okay, check this out. Let's say your limit is 10, and the counter in Redis is sitting at 9. Now, two requests, A and B, hit your servers at almost the exact same instant. Both of them ask Redis, hey, what's the count? Both get back the answer, 9. Both of them think, cool, 9 is less than 10, I'm good to go. So request A adds 1 and writes 10 back to Redis. Then, a millisecond later, request B does the exact same thing. The final value is 10. Do you see the problem? We let two requests through, but the counter only went up by 1. The limit is totally broken. So how do you fix this? The answer is something called an atomic operation. Atomic just means it's one single uninterruptible step. Instead of doing a separate get the value then set the value, you use a single command. In Redis, that command is incr. It tells Redis, read the value, add 1 to it, and write it back. And don't let anything else happen in between. It's a single, bulletproof transaction. This completely wipes out the race condition and keeps your counts perfectly accurate. For anything more complicated, you'd wrap it in a Lewis script to keep the whole thing atomic. Okay, we've gone through the theory, the architecture, and that huge race condition pitfall. So let's boil all of this down into a practical checklist you can actually use when you're designing your own system. First thing, pick the right algorithm for your traffic. Don't just guess. Second, use a fast, centralized data store. Redis is the go-to for a reason. Third, and I can't stress this enough, you must use atomic operations. This is not optional. Fourth, have a plan for when things break. What happens if Redis goes down? Do you let all traffic through or do you block everything? Decide that ahead of time. And finally, monitor everything. You need to see what's being allowed versus what's being rejected. This is how you'll spot problems like hotkeys in Redis or even weird clock drift issues between your servers. And that really brings us to the final big picture question. We've been talking about the rate limiter as the gatekeeper that protects your services. But who protects the gatekeeper? How do you make sure your rate limiting system itself doesn't become the single point of failure? That challenge, making the gatekeeper itself scalable and resilient, is one of the toughest and most interesting problems in all of system design. Something to think about. Thanks for joining me.